In this last video, let's still have a look at the possibilities to use the VAR for forecasting purposes. And to that end, it's important that we first define the concept of Granger causality. So let us start from our YT vector, but let us rewrite our VAR model where I split up YT in, let's say, a subvector XT and a subvector ZT. Now, XT is set to Granger cause ZT if ZT can be predicted more efficiently when XT is taken into account. So in other words, when XT has incremental predictive power for ZT, where incremental means predictive power in addition to what is already contained in the past of ZT itself, well then XT Granger causes ZT. Now, let's look at the opposite setting. When would XT not matter for forecasting ZT? Well, when all of the corresponding coefficients of XT in the equation for ZT, so these guys over here, would be equal to 0, when they would not matter. Then XT would drop out of that model equation and there would be no effect on ZT. And that is exactly the null hypothesis of no Granger causality that we would like to test. So how can we test this hypothesis in practice? Well, we can rely on any of the three methods we discussed before. If we think back of the LM statistic, is it then easy to obtain this statistic in the case of the no Granger causality test? Well, remember that the LM test relies on the restricted parameter estimates. So we would have to impose these 0 restrictions here as laid out under the null in order to get the restricted parameter estimates. Is that easy? Well, in this case, this can be easily done by just dropping out the predictors XT from the equation for ZT and estimating that equation by least squares. You can, of course, also rely on the other hypothesis tests, but in this case, I just wanted to point out that the LM test is still quite easy to obtain. Now, from the definition of Granger causality, we know that it's not about true causality, but actually about incremental predictive power of one, possibly a set of variables for another. So let's finally have a look at how we can obtain forecasts in the VAR model. A natural question that arises here is, how can we obtain a forecast for the next period for one of the variables, or even for the entire vector, since everything is jointly modeled? And what is the best possible forecast we can obtain? Now, to answer that last question, we first need to formally define the so-called mean squared forecast error. So let's first introduce some notation here. Let's denote the forecast made at time point capital T for time point capital T plus 1 through this notation over here. So we make use of all available information until time point capital T, as indicated by this, let's say, conditioning on T. And then the mean squared forecast error is defined as the expected difference between the actual value and the forecasted value. Or in other words, the expected squared error we make in forecasting this random variable, when we make use of all available information up until time point capital T, as denoted here by this information set XT. Now we can show that the best possible forecast for Y at time point T plus 1, taking all information until time point capital T into account, is given by this conditional expected value. of yt plus 1, where we make use of all information available until time point capital D, as collected here in this xt. Let's have a closer look at the derivation of the optimal forecast. On this slide, I'm going to write this conditional expected value more compactly through this new random variable z. And let's just start simply from the definition of the mean squared forecast error, which is nothing more than the expected value of the squared error between the actual and the forecasted value. Like we did earlier in the derivations for the maximum likelihood estimator, since I need to say something about the optimal forecast, I would like to bring it into our derivations, which I can do by subtracting and adding back the conditional expected value. Then I can regroup the terms. I take the first two together and also the last two together, and I expand. Now, the expected value of a sum is nothing more than the sum of the expected values. So I have in the end these three expected values over here. Let's now take a closer look at the last term in red. You can notice that this last term is only a function of future innovations. And these are unpredictable. Remember, we work with the zero expected value assumption for the innovation. So this last term is 0. That means that I only have the first two terms that are left. Now, what is the first term? The first term is nothing more than the definition of the mean squared forecast error for zt plus 1. It's indeed the squared forecast error of zt plus 1. Since the last term is a squared term, it's positive. So the left-hand side needs to be larger than or equal to the right-hand side. When can they be equal to each other? Well, they can only be equal to each other if this last term disappears. So when the optimal forecast y star for time point t plus 1 made at time point t is equal to zt plus 1. Or in other words, if the optimal forecast is equal to the conditional expected value, which proves that our forecast error is minimized when we take the optimal forecast equal to the conditional expected value. Knowing what the optimal forecast is, we are ready to compute them for the VAR. So we need to compute the conditional expected value, taking into account the information set at time point t, which is nothing more than all past information on the value, on the variables in y. Inside the expected value, I just plug in the model equation of the VAR at time point capital T plus 1, which gives me this sum of the previous p observations. And we have, of course, the error term at time point capital T plus 1. Now, since we compute the forecast at time point capital T, everything until time point capital T is known. So they are no longer random variables. They have realized. I know what their values are. Since these are just values or constants, I can take them out of the expected value as I do here, and I would be only left with the expected value of a future error term, an innovation, which is of course 0. So that gives me my final expression for the optimal forecast for the next time point, so the one step ahead forecast. Of course, in practice, I can't make use of this optimal forecast since I do not know the values of the unknown parameters, phi1 up until phi p and the constants. In practice, I first need to estimate all of these parameters, And so if I replace the unknown parameters with their estimated values, I arrive at the observational forecast denoted by the hat over here. Now, in the tutorial assignment, there is also an exercise to practice a bit with computing the forecasts in a VAR. Also, for multi-step forecasts, so this slide was computing the one step ahead forecast, but you can also look at the forecasts 2 steps ahead in the future. All right, so we are also at the end of this lecture week. You've seen all the material to go through the chapters needed in Hamilton for more detail if you wish. And you also have everything in place to prepare for the second tutorial. Good luck.